Okay, so some of you were not there last class. I am still, so we did a coding exercise. Did any one of you try that? What of you had a chance to try? No. So we'll continue with some of the basics, and then we do the coding exercise, and that is directly translated to your projects, and that each one of you are doing. So, and in today's class, I will do a small revision on what we learned last time on what are neurons. And then I would introduce you what are activation functions, what are loss functions, and what is gradient descent. These are three new concepts we will learn today, and then we will do a new coding exercise. Now, let us begin with something called what are neurons. So last time, we did something on what are neurons. Just a second, let me hide my coding panel. Okay. So this is a classic diagram of neuron on your screen where you have a blob-like thing, a neuron, which you famously called, and it is connected to input parameters x1, x2, and x3, and it gives you a y output. Last time we discussed exactly what happens inside the neurons and how it is working. I will quickly remind because the activation functions are directly linked to last class. So here, as an input, you know that it is dependent on parameters x1, x2, and x3. And these parameters, now they are multiplied with their weights, and then they are added up in neurons. And then the final output is obtained. And we had this case where, we took a data case where we had three different parameters. And here we have a parameter of X parameter as an age, and Y, that is your probability of dementia. It is given next to the age. So from this, we know people with a less age, they have no dementia, but people with higher age has a dementia. So this kind of data is given to you. That means the final Y is dependent on a parameter here, X1. So the first thing that comes to mind is to plot this curve. And when you plot this curve, you get this, here is the probability of dementia, here is the age, and you simply this is your linear fit here. You try to fit this database. And what do you get? You get a relationship like that. So here you see that the final output, which we are looking at, we want our computer, we are training our algorithm to be trained for the probability of dementia. And it is directly linked to your slope value and your bias value. And today we would be looking at why these weights, how can we adjust these weights, how can we adjust this bias, and this is your final output value that we get. And so I gave you an example last week. If I give this curve to different people in our class, we will draw a line in a different way, right? This was a clear message that, so somebody would draw a line like this. Hold on, because I would go on weights immediately after this little concept. Why I'm drawing a line, but it's not visible on your screens. Okay. No clue. This is selected all lines that I drew and there, Okay. Let me move to the next slide, maybe to understand this concept here. So this is now your dementia is dependent on another parameter. And if, again, if I tell, if I tell Merve to draw a line, she will draw a line like this. And if I tell Ryan to draw a line, maybe he will draw a line like this, whatever you think. So these simple things, it gives what it will change. It will simply change this. This would simply change this relationship of your parameter with your final probability. And this slopes and these bias are what are finally changing your weights. Now, how do we do it in CNN? Now, this was the third parameter we have. So this is the diet. And again, this is the probability of dementia. And we had a relationship like this, where higher your junk food per month, you will have a higher probability of dementia. That means related to a poor diet. And we got a relationship like this. So finally, what we are doing here is, this is inside the neuron. We want the final probability of dementia, which is simply the addition of probability that comes from each parameter. So here I can add y1, y2, y3 till yn if I have n parameters. And every y1, basically, it is telling me a probability that dementia will develop because of that particular parameter. And this is the very classic formula we have, y is equals to wx plus b. And here you see, to have the right relationship between y and x, what we have to adjust is weights and bias. So this is the step one that was happening inside the neurons. And last time I did a calculator where I showed you that how inside a different neuron, when you have y is equals to minus 0.288, y is equals to 0.402, I applied this into a sigmoid function and I obtained those values, because I could not take my decision on a random function. So when I have a function like this, that means all my y probabilities, I converted from 0 to 1. And then in the middle, I take this line, and it is easy for me to take a decision that below 0.5, here people will have no dementia, and here people will have dementia. So overall, concluding this, inside the neuron, we have two things. One is simply y is computed by this formula here, and then the activation function is applied, which converts your final y output between 0 and 1. And this helps you to make a more exact decision. Now, coming to today's class, what are activation functions? So you learned from sigmoid that we convert the y range from 0 to 1. And you can choose in your neural networks which activation functions you want to put in. So for example, here I showed you an example where it converted the range from 0 to 1. You can choose another neural network where you will, choose a range from -1 to 1, depending on your problem. So this is a classic example of neural network on your screen. So it is simply telling you that in the beginning, you do this simple formula here. And then there is an activation function that happens inside the neurons. And then your final y output is fed into another layer. This is the same layer is repeated. In the last class, if you remember, I showed you that our neural network consists of input, hidden layers, and the output layer, right? Now, this is the input parameters. This is here on screen is layer 1. Now, this is layer 2, and this is your final output. And in the coding itself, we created many layers last time, if you remember when we did the coding. So every layer, the same thing is happening. You have initially that simple formula where you add your parameter multiplied by their weights, and there's a bias, and then everything passes through the activation function. You will have some Y output, then this goes inside here into the second layer, and then the same thing happens. Now, there is something known as firing of neurons. So these activation functions are also responsible to make the neurons fire or not. For example, here you have this value of Y that we computed, right? In one case, it was minus 0.28. Then you entered into the activation function, and the value became 0.4. If I want, this is a threshold that I can play with, and the places where my activation function value is 0 or less than 0.5, I do not want my neuron to fire. I would only like those neurons to fire which has a value above 0.5. These kind of conditions I can set in, and these activation functions therefore are one of the ways in which you can literally play with the threshold, let your neuron fire, and get it to the next layer. Now, common activation functions that you would use, it's simply you're converting your Y into a range. So here you can convert it from simply, equation fx is equals to x. So it's something very intuitive, and the range is from minus infinity to infinity. And if you last time you put into sigmoid form, and this time you're converting into a linear function. And here again, if you have to take a decision, it's slightly complicated that where is the center. So these are generally not used for binary classification. As in our case, we have the example of void and the background. We never use linear activation functions. These kind of things are used where your output is varying linearly. Now, this is another one that, this is a sigmoid or logistic activation function. Here, we already talked about, I showed you the calculator last time, just that range is between 0 and 1. Now tell me, do you see any problem in this activation function? Like, what do you think? So here, you see that in the cases where your Y value was becoming negative, it is constantly bringing it to 0. This is more clear in the next slide here. So similar to sigmoid function, I will come up to this explanation in the next slide. Now, similar to your sigmoid function, we also have a tan H function. What is the main difference? And you would be using them in your CNN during coding. It converts your 0 to 1 into -1 to 1 range. That is the difference, main difference. And then there's a difference in the shape of the curve. Now, what is the main thing that you notice in, like, here? This is one common activation function. Okay, let's look at here. This is like the #1 activation function used in all CNN that are, you will see the codes available. So in this activation function, you have comparison here with sigmoid and ReLU. So ReLU, which is a rectified linear unit activation function, it is the most used activation in the world right now, since it is used in almost all CNN or deep learning. Now, what is the good and bad about this ReLU? So ReLU is half rectified from bottom. That means fz becomes 0 when z is less than 0. So what happens? Remember this table of ours? So if I put and start applying a ReLU function into my problem, then this y 0.288, anything, so y, whenever your value is less than 0, then your final answer becomes 0. by using ReLU. So if you have y is equals to minus 0.288, in this one, you are making your value equal to 0, right? Also for this one, y is equals to minus 0.348. If I don't use sigmoid, I'm making my value to 0. So yeah, so we don't see the difference, right? So we don't know where to put this center threshold value, right? Where we were making a decision that below 0.5, we will have your, it was Alzheimer, the disease that we were talking about, dementia, that we will have dementia. So this is a big problem. In most of the activation functions, we have a problem of vanishing gradient. Here also it starts occurring, when the negative becomes bigger, when it becomes a very big number, but it still does a good job in the beginning of it. When it becomes a very negative number, then also it starts becoming flat. So this kind of problem, it exists, but what happens is we are really saving on a lot of computation here. So then there's a trade-off. Now, to solve this problem, leaky ReLU problem, what they did, they come up with a new function. They come up with a function called leaky ReLU, in which this kind of function, they started giving it a little bit of tail here, or a little bit of leak that they're calling. So in this one, all the negative numbers, finally, you are able to get a value and you're able to segregate between two negative y values. So I know this information is new to you, but when you create your first coding, this is the main terms that you would find ReLU. I also showed you in my last coding. We use sigmoid, we use ReLU. These are the common activation functions. So when you start choosing an activation function, you ask yourself. So can anyone comment now on vanishing gradient? What can happen if you have a problem of vanishing gradient? Any remarks, any comments, any discussions? When the model stops learning. Yeah, because it cannot separate between two negative y's. Everything, the value is coming to 0, right? Okay, with this, we are going to our next topic, which is what are loss functions. Any questions, guys? This all is very new. It's clear? Yeah. Okay, what are loss functions? Any idea before we begin? What are those? Okay. So now we will move actually to CNN. Until now, I was showing you the basic, very simplified problem like this, where your answers were matching, right? Now here, in this case, we make a decision that 0.428 is your y value, and we start making a decision. But your actual y value in this case was there is a table missing here where your actual value is provided, right? So for example, okay, this is in the next slide. For example, here you see, you have this entire database where you are providing it age, exercise, junk food, and it is giving you the probability of dementia. Now you will have a final y predicted value, and this is your final y value that are not same, or they are not equal to each other in the beginning. And I would now tell you that if it is not equal to each other, and when you find your answers, the difference between the actual dementia value, which is 0, versus what you compute could be 0.5 or 0.6. That difference is known as loss. It's very straightforward, right? Now let us go one by one and try to understand this concept. So what are loss functions? Okay, before understanding this concept, let us quickly remind ourselves about what are partial derivative, because this term would be used again and again. So everyone knows about what is a derivative, right? If you have a single parameter, right, that y is equals to fx, that means it only depends on one variable. You simply compute, dy by dx this way. Very simple, like basic math. In partial derivative, what happens? We all know since high school, right? If your y, or if your final function is dependent on two variables, like here on this curve here, it is dependent on x and y. Then how do you find that how this final function is varying with respect to only one parameter? Either it is varying with respect to delta x or delta y. Now, you simply do what? If I have to calculate del f by del x of this equation, what would be the answer here? Can anyone tell me? 20. And here the answer would be 4. So what we did, we simply made everything other as constant and we computed it. Now, isn't the same thing happening in your neuron? You are trying to calculate if I do delta y by delta x1. That means your final output is varying on one parameter. And I can find these values. So that means in our previous case, delta f was dependent on age. If I do, I can calculate that value. Let us see how we calculate it. This is the famous slide now. We all know it very well. This was our problem that we are constantly referring to. Now, this was the value of y inside the neurons. And if I start putting all these, if I expand this formula and put the values of y1, y2, y3, what I get finally is a function like this, isn't it? And now, if I start taking a partial derivative, then what will be the value that I will get for delta y by del x1? What would be the value here? 0.023. And for exercise, we will have the value minus 0.053. And for diet, I will have the value 0.047. That means mathematically, it is possible to have a relationship of the final output with your initial parameter. Having said that, it means it is highly possible to optimize each of these relationships as well, because it is directly linked to the output. That means if I open up this curve and here, one of you, as I told you, different people will draw different lines and it will give you a different value of weights. That means so this is also known as back propagation, where I have the final value and my final value is dependent on my initial parameter, and I can optimize this value till the time my y comes nearly to my ground truth value. That means to the value that I want, or to the value that matches with the true answer, right? Now, this is something here you see that why I'm emphasizing here. Isn't it really great that you have a simple equation like this, and it could be n parameters, and you are able to tell by these simple equation the influence of one parameter to the final output value. For example, by using these equations, I'm able to tell, or at least come very close to the final answer, by what age I can choose any age, and I'm able to tell the final answer. It will depend on other parameters for sure, but at least it will give me a relationship, right? So these kind of relationship where each parameter and final output are related to each other are extremely powerful. Now see, I have applied the same thing to another data set where you have a flight price that depends on on miles. It also depends on airline brand. It also depends on destination. Now this flight price, it would be a function of all these three parameters for sure. And if this is the final kind of relationship you have in your neuron that you can have, it's just an example, a hypothetical example, then the flight price as simply is equal to 5 by taking your partial derivative. So my point to bring this kind of data set is simply to tell you that you can, by doing these kind of equations, you can simply tell away the relationship between a single input parameter to your final answer. And remember, in your neural network, you don't have 3 parameters. This is just an example case. You will have 100 parameters. Now, how these weight updates are happening? So in the beginning, when you define your neural network, you are simply defining it on your code. And in the beginning, you initialize a weight with a random number. So here on screen, what I have done, so this is just a top part, is just to give you an overview of what we are doing. Now, if you focus here, so in the CNN training, we do weight initialization. So in the beginning, you have this equation Wi xi plus b, and let us assume that I take the weights W1, W2, W3 as 1. And I take the bias equals to 0. And this is something I literally do. I simply create my neural network and I choose my weights like this. So you have to see it is happening in your coding. You are not creating Excel sheets now. And when you initialize this weight as 1, 2, or 3, in your neural network, you will do a random weights. Then you have an output, say 0.56, right? And your actual answer, here, I just fed the row first. So it was age 23, exercise 1. And here, your diet, here, it's a misprint. It also has to be 1. And finally, you are getting a number as 0.56. But your actual number should be 0, right? So this is your started beginning. Now, how to bring this number to 0? Now, you already know that these are not the real weights, right? Now, how your code or your algorithm comes to finding the real weights. So you just went there, you input your Excel sheet like this, you went and you created a neural network. Neural network will automatically, add up all the parameters, and you choose a parameter of initializing weight as a random matrix, and you come up with this answer. Now, when you look at your error is 70%. You guys are not happy. 70% error, that means I don't know what I'm doing. It's just an example. Now, that means maybe the weights that were chosen, they were wrong. And we want to really bring these lines to maybe to a red line or any other more suited line for this fit. Now, what happens is the same condition, absolutely the same one. Now your neural network will take the second row. In the second row as well, it has 26 age, 14 exercise, and 12 junk food per month. So the final answer that we are getting here is 0.36. Again, the error is pretty high. This is error 2. Similarly, it goes on row 3 because weight initialization was done. It was the same weight, and it computes, and this is your error. Finally, individual error that is computed for each data is known as loss. And if you add these errors, this is known as cost function. And this is a common terms that we use, loss function and cost function. Cost function is just an average. Now, this is a kind of path that your neural network takes. You define it, it keeps on computing errors. Now, once your errors are, you have run your data and your algorithm has passed through all the data at least once, that is known as epoch, and it has gone at least once here, then you get something as a total error, right? And this is your total error here. And now, we have a lot of error in our network, and you know that you are not successful. Now, what you will do, or what your network would do. So theoretically, we can choose different loss functions. Why do we choose different kind of loss function? You have simply a value that is a truth value, and this is your predicted value, and you compute it. Now you convert it into some kind of mathematical function like this, an easy mathematical function. And you compute it. Why do you change and select different loss functions? Any idea? Like I can simply, any mathematical problem, why do you choose a different kind of loss function? Have you done any problem like that? Why? If I simply give you Excel sheet and I tell you to convert it into square, your loss, convert it into square, convert it into a cube, or convert into a log. A lot of Excel sheet. We do standard deviation. Why? True. For example, I want to measure an error between two situations. So it definitely depends on the kind of data I have. In some cases, I will simply choose standard deviation. If I am choosing population, for example, I have plotted the population in the Gaussian term with respect to, with respect to any parameter on the x-axis. Then maybe I'm choosing a standard deviation that tells me the deviation from the mean. So my point is, we convert these final values into different other functions so that it starts making sense to your model, right? Now, in this one, we are choosing into a mean square error. And mean square error, what it did, earlier it was a straight line because it is an absolute y minus y bar. So it was a straight line, and mean squared error made it into a curve like this, a shape like this. And there are other loss functions that you could choose, right? So these are the common loss functions. And I'm emphasizing here because you would use this term in your coding here. Last time I taught you how are you using, optimizer, and you were using losses. And it was mean absolute error. Sometimes you will use mean squared error. And you will use it depending on your problem. I will get into it in later slides. But look at here, the simple, so this is here, mean absolute error, which is given by an orange color here, right? Mean absolute error was nothing. It was y minus y predicted. And if you plot it, it simply is a beautiful orange line in both directions. And now you can convert the same error into mean square error, which will become a red line, right? Now there are people who publish a lot of papers and they say, okay, we propose a new function for this problem, that is a Hubbard. So they plot a curve like this. And now there was a paper literally where, they say that it would converge better. This function is better and this function is better. Now, for you as a beginner, in large cases, you will, choose something known as mean absolute error or mean square error or cross entropy error. Now, so this is why we have different loss functions and people get very confused. Why do we have a loss function? Now, coming back to our initial problem that how the weights and bias are updated, right? Now, does this statement causes trouble to anyone where I say your predicted value, that was your final value y, is directly proportional to weights and bias. Remember, this was our final equation here. And this y, it is directly proportional to your weights for each. If we do partial derivative, okay, let's try to do partial derivative and keep our equation till here, right? Each final value, it depends on your weights here. That means if I make this value as 3000, that it will have a direct impact on my y. It also depends on my bias. If I make the bias value very big, the final y would change, right? And it is valid for each case. It is valid for W1, it is valid for W2, it is valid for W3. It is also valid for bias 1, bias 2, and bias 3, right? So what your computer does, immediately you compute this error and you plot it with your any initialized weight matrix, right? So initially you choose the number 1 or a random weight matrix, and you have computed these errors, right? You have computed this error, which are absolutely wrong. Your errors are very high, your models are absolutely wrong. Your computer, your algorithm, what it does is it tries to simply plot them because it needs a starting point, right? It simply would plot, your loss error with any of these parameters. Now with this, I think I made my point that what are loss functions? Why do we plot them with predictions? We can, because this is your actual predicted value. We can plot them against your biases, and we can also plot them against your weights because there is a linear proportionality relationship, right? I can choose any matrix, right? But these are the 3 numbers where I see that, there is a dependence to it mathematically. Now, saying that, I move to the last concept for today's class, that what is gradient descent. Now, this is a universal concept, and this is the concept which is used to update your weights. Now, we were till here, right? This is the problem that we were discussing since beginning. We have computed the error. This is the error for any row. And now I have added the error 1, 2, 3, 4, 5, 6, 10 till the end row. And I have got my final plot like this, right? And I have chosen a loss function. Let us say in this case, we have chosen a MSC that we choose. Now, how are we updating the weights? So you see, so this is a cost function. I told you that average of loss function is a cost function, is the same thing. It's the loss. So loss is plotted against your weights like this. That means your loss is so high if you plot it, right? And why? This is also following this shape. So you had an absolute error like this, which was orange shape. You converted this into MSE. And you know that predictions are directly proportional to your weights. They're directly proportional to your biases. So everything follow this shape, right? Now, when you plot it, you see that error is very high for a particular value of weight. And what does your algorithm do? So what do you want? You want that your weight should reduce, right? And your weight, what do you want, your weight to reduce or your error to reduce? You want your somehow that my error should reduce from here to here. Now for that, what do? We have to somehow bring the weights to a level when your error becomes 0 or error becomes minimum. I don't know if I can do 0, but if I keep on going down on this curve, I can reach a point where my error becomes 0. And that would be the best value of my weights, right? And I want that. So now I'm here. This is something happened because I chose a random initial weight, right? I did not know. I did not know that my value was 0.28. I chose the value as 1. And I plotted these errors and I am here. Now, what mathematics comes to your mind when you want to go from here to here? What mathematics you think of? If from this value of weight that is here, I subtract the slope of this curve, that would give me a value. I would reach here, right? If I subtract the further slope value, this is just a value of a slope, I would reach this point. I subtract this value of slope, I would reach this point. To go from here, if I continuously subtract it, I would reach this point, right? Which I want. Now, what your algorithm does, so this is something, if I give it to some person in the class, say Merve, maybe she starts, take 2 points here. She starts taking a point here. Now, I would be slowly, So she will take a point here, and then she takes a point here. And she says, I have my weight here, right? Which is my value. Say, this is my value here, 2 value, just an example, right? It is a value 2. And now she wants to go to a value, which is a value 4, right? So what she will do at this value to 4? She will simply have this value 2. She will add a difference of these 2 values. How much she has to go down, right? That would be a slope of your cost function versus your DW. 1, right? Right? And if I give it to maybe to Ryan, what he does is he takes this point here and he takes a direct point here and a direct point here, right? Just 2 points. And he computes a new value, 2 plus the slope now between this point. So I just mark here by names. So this was maybe, this was like maybe point of Merve. This is the point of Ryan here. So these 2 guys are sitting in front of me. That's why I'm choosing their names. So this is here Ryan chooses and he computes a different gradient, dc by dw1. You know what is a gradient, right? Mathematics. It is a difference between 2 points. By here, it would be the difference between this. For Merve, it would be the difference between this, right? And you compute and you get to the final answer. And maybe I give it to Tommy. He says, I am very sensitive to what you're doing. I will take very close points and I will go slowly. This kind of thing is known as learning rate, where you are going from top point where you choose your speed to get to that point. And a slow learning rate will give you many points and your values would be more correct, right? So finally, the bigger range a person is choosing is multiplied by something here because, depends on a person, right? It would be a learning rate here. That would be a number. Some people will want to give, as I told you, bigger spacing. Some people will give smaller spacing. So we multiply here by a number. So we agree that this is how, even mathematically on your Excel sheet, you can reach from this point to this point. And if this would change, this is ultimately the value of the slope that we had, then your bias would also change, right? All the 3 things are linked to each other, right? Now, this is known as weight update. Ultimately, I was going from higher weight and I wanted to subtract something to get to the lower weight, right? Here is my point, right? Where I want to go. Maybe not, I'm still not in the center. And we want to go here. So this is the classic equation that your algorithm follows. It's the classic equation, like on which all CNNs are based. It's like the fundamental, as if I'm like right now telling you 3 Newton's law. It is as fundamental to your CNN that you cannot forget your Newton's law and you cannot, build physics without them. It's a similar way you cannot build CNN without these equations. You compute error, you plot that error with respect to weight. people get confused. Why are we plotting with respect to weight? You can also plot with respect to bias. You can also plot with respect to your final predicted value. And these are the curves that you would get. And you simply want to go to here. And this is the equations that a computer follows and get you from here to here. Right? Any questions here, guys? Yeah. And now this is simply a thing on learning rate. You put this value in your CNN while training. Never put very high learning rate. With high learning rate, as I told you, what could happen is you are choosing a learning rate where you are going from, so this is an example. This is a very high learning rate. So you're going from this point and somebody took a very high learning rate and is directly going to here. And then you are going here. And then you are going here. And ultimately you miss the minima because your learning rate was so high. Too large of a learning rate caused drastic updates, and which would lead to a divergent behavior, but not a convergent behavior, right? This learning rate is optimal. So you have to be somewhere in between. The optimal learning rate swiftly reaches the minimum point. Now, if the rate is too low, it will make many updates between reaching the minimum point. That means if you're too careful as well, it is a problem because you are taking too much time. You don't need to move that slow, So this is, you have to be somewhere here in between. Now we will do our practice code. So we know something about learning rate today. We know something about the gradient descent. And this is like the fundamentals of your neural networks that I have been dealing with. So any more questions anyone has before I start doing coding? So kinds of clear the entire neural network thing. It is easy if your fundamentals are clear. If you, once your data comes out and you don't know why I'm plotting against weights, why I'm plotting against bias, how it is updating weights, why I'm choosing this learning rate, you would be in a kind of a messy situation. Right? Now, here with this another remark, because I want to reach here in a very smooth way. Finally, the objective is to have the minimum error. That is why the shape of loss function is very important. So when you choose these loss functions, for example, here was an example of various loss functions. And I told you, people are debating here. So the biggest question is, there was a paper that I read a couple of weeks ago, that should my loss function should have a bigger gradient or a smaller gradient? Because if you have a bigger gradient, you're moving pretty fast. So it is the initial choice that you make, it changes everything. So now I will show you today live problem where you are choosing different loss functions, and that would change your results. Any questions, guys, before we move to another problem for CNN? Yeah, so it's here. I forgot to add it. This is your cost function. This goes one by one. I think once it finds out for one cost function, I think it stops. This is like, and then goes to another one, and then, because it individually considering all parameters, right? Hi, Sydney, are you online?
Yes, I'm here.
Okay, any questions?
No, I'm good.
Okay. Now I would start sharing a new screen with you. So for this problem here, let me go here. So let me quickly show you. We are doing a coding on so let me share my screen. So this is a problem of cat versus dog. I just clicked on the link. Finally, I'll upload all these lectures because I was making videos, I was not uploading. But again, I should provide you these lectures. So here it is cat versus dog. So you'll get used to Kaggle or YOLO for everything. You start downloading data here. You just download it. And I have downloaded this data. And what does this data consist of? I think in one of the classes earlier, I showed you that I downloaded this data, and this data, it consists of many images of cats and dogs. If you guys remember, I showed you. Let me quickly find the data for you guys. So here we have a test set and a training set. And I think I emphasized last class, what is a test set and what is a training set, right? So in the test set, I have 1,000 images because I'm testing the model, right? And they are images of cats and dogs. And then the training sets, I have 4,000 images, right? So I got 4,000 images of cats, 4,000 images of dog. This is all my training set. And then I'm testing it with 1,000 images of cat and 1,000 images of dogs. So what I'm trying to do in this problem, I'm trying that to train my network that any cat or dog I provide you from all over the world should be able to tell me that this is cat or this is dog, right? This is a beginner problem. In the same way, it can be used in a security problem. If I'm able to say this is male, this is female, any airport security can tell immediately, any photo that comes, right? So for you, you should be able, this problem will directly relate to the case where you would be able to say any microscopy image that comes, it is a void or it's a dislocation. Similar methodology is done. Now let us, so we just simply create a folder on our computer, download this data sets from the website I showed to you. Here, link is provided, and you can start doing. Okay. How many were you able to download the uh, yeah, yeah, yeah. You guys have it? How about you guys? You guys have it? How many people have it, right? Okay. Let us start. I think Jonathan, you missed last coding. Have you ever any familiarity with machine learning? Yeah. You have little familiarity with how this CNN works? Yeah, okay. So what I did right now, I just, these are different libraries, right? Uh, so guys, it's important. I emphasized on all these terms last class. What are sequential model? What are convolution layers? What are max pooling, dense, and flatten layer? I can keep on emphasizing on it, but not uh, not sure that if I should emphasize again. Any questions here? So these are different maths library, right? Pandas, NumPy, Matplot, and these are everything you are loading from your TensorFlow. TensorFlow is one of the biggest libraries we have where all these models are stored. And these are provided to us by Google. People can also use PyTorch. PyTorch is provided to us by Facebook. So these are the biggest libraries available, where you can create these models. So we are doing a sequential model. Can anyone remind me why are we choosing this term sequential? Because last time we told that, everything is a sequential model from input layer to your hidden layer to the output layer. In the neural network, everything happens in the sequence, right? You have your input, then you have, you have computation, then it goes into activation, then it goes into the second layer of neuron, and then finally your answer comes. So that's why the term sequential. Convolution, guys, right? Convolution is the term that is coming from your convolution layers. Then we have a pooling, and then we have dense and flatten. And then these are the different libraries I have just uploaded. Now, I showed you my computer, and these are the path to your training. So I was in my desktop, and I was in the, I just use the same address. Wherever I am in my desktop, if I make a folder called dataset and put it inside, I just give it a valid address here, right? So now I have imported libraries. I have connected my Python worksheet to the folder, right? Now today I will do something called data augmentation. So you saw that I have 4,000 images, right? Now, some people would say that 4,000 images are too less to do anything, right? Now, 4,000 images are too less to do anything, so we want to augment our data. So augment our data would mean that I will use certain commands where here it would rescale your images. So I have 4,000 images, and next 4,000 images, I slightly rotate them. I slightly flip them. Remember, we are trying to train our computer by giving it many images. And if we create one more set of images and we merge those images into the previous data set, and then the image number would become from 4,000 to 8,000, with some of the images looking very similar. So in this way, we are training our computer much more better. So this is a very classical, code we use: train, data gen, image data generator, right? And this is rotation range. We are rescaling them. Sometimes we can flip them. We have a little shear range where, you're just shearing it. And this is your fill mode. So this is all our little details on data generator. If you have 4,000 images, you have to, but if you have 80,000 images, you don't have to do anything. Same thing I'm applying to test data gen. Okay, I've applied that. Now, what happens here? After augmenting the data that you would do in all your, in majority of your codes. Now, tell me what is this one next in anyone? what I'm doing here. Yeah, so what I'm doing, what are these terms? Mhm. And what is the batch size? Okay, very good. Yeah. So we simply connected here. We see here everything is Python is a very very easy. This is one of the easiest coding language I know. It's very similar to how we write English. So here we created this train path and test path, and the names are important. Here we created train data gen and test data gen. So I'm simply now, you know that I just simply connected it to my drive where images are stored. And here I'm applying data augmentation. Now, all these things, finally, both of them, they together create my training set. So in this, I'm creating my training set and I'm giving it a name training set and test set. And if you constantly give new names to it, it is like, you're today calling your data set as data set 1, tomorrow data set 2, and then you are calling it data set 3. So the last name that you call, it would be your final name where tests would be performed. Now here it's a training set and you are just giving it an address that this is a train data gen. And these are the 4 categories we are given. Here we are simply defining the complete address to your data set. So it's a train path, which is here coming from the directory you have created. Image size, you know that size of your image is 150 by 150. In some cases, it would be more. You have to find out that size by simply going on, any of your image software, and it would tell you what is the pixel size. Now, here important information is batch size. So in one epoch, so if I want, I can give a bigger batch size. I have given here 32. That means in every epoch, in how many batches my algorithm is passing through. Now it is passing at a batch size of 32. And now we know that we are doing separation between cat and dog. So it's a binary problem, right? In the last case, it was the digit code that you remember, it wasn't a binary problem. It was, you were doing 10 cases, right? You had 10 outputs possible. Here, there are only 2 outputs. Similar thing, you will do it to your test data sets. Okay, now come to the interesting part. Okay. Now you will give me answers to my questions. Now I'm creating the model. So when I run this, my previous cell, it tells me found 8,000 images belonging to class 2. How they became 8,000 here? Because it is simply trying to, in the training folder, so this is also a little bit important when you're a beginner. So in the training folder, if you know, I had a data set in which I had cats and dogs, right? So it is simply compiling the information of all of them and making it 8,000. So now you're here. And this is, so it is simply telling you that this is your training set. Now, can anyone comment on this one? We are simply creating a CNN. We are initializing it. What are these commands here? I went through them in the first CNN class that we had, where I showed you a presentation. What's that? Yeah, just the CNN model, how I have created it. This is a CNN model. So I have created a model that is a sequential model. And then I have added convolution layers to it. They are 3 by 3, 32. So let me open this quick presentation for you that would help you to understand this code. So if you remember my initial So how many of you remember this presentation that I presented on the first time? Right? So what is happening here on this one here? Let us try to quickly review it because then I would run the model and it would be trained. So this is where every, all kind of understanding is, and you will be started, developing them. So let us try to quickly review it. So this is a very classic example that you will do with your any microscopy image. So what is happening here is you know how to uh, you know how to draw in PPT. You cannot draw in PPT. Okay, we can. So you see this slide, most of you, there's a slide that is presented, right? So this is your CNN. You had this initial image, right? And now this initial image, so first of all, this is important here that this model is a sequential model, right? Because everything is in the sequence form. And to all the people who will be doing coding, these are the important steps. So you call this model sequential. Now, after adding this model, you are doing something on the second step, that is your convolution. Now, in the convolution, what is happening in the convolution? Remember, I told something about feature extraction. Multiple times I've emphasized here on this presentation. That in the beginning, I call something my initial weights in form of this filter. These are actually my initial weights, which I call, and I try to put this on your image, which consists of number, and there's a multiplication that happens. So the term convolution, if you remember, means that by English that they are literally, binded together. So that is why we use the term convolution. So this is getting multiplied to this, and I can choose as many number of filters I want. So these filters, right now I've chosen a filter by 3 by 3 matrix. So you now start thinking in terms of matrix here. And now this will constantly, we slide this matrix here. So this is what is exactly happening. We have 32 filters, 3 by 3. that I am sliding, right? So this is, I'm sliding with this one, right? So I have 33 by 3 small thing. I'm sliding on 32 filters because I am doing it 32 times the same thing. You have a better answer. You can choose 64, you can choose 128, you can choose what number you want. Yeah, 32 filters. 32 filters are slided. Now this is your input shape. Can anyone tell me why there is a 3 here? So these are your colored images on screen. That were the images of cat and dog, right? So those are colored images. So these are RGB channels, 3 channels. Then the activation function that we are giving is a ReLU here. You can choose anyone. Remember ReLU, we had a curve like this that was going flat. Wasn't very happy. Then you can choose as many layers as you want. So if you could see my pointer here, there we are 2 layers here, 1 and 2, right? So depending on the number of layers you have here, this one is my first layer. Then I have added another layer. So I simply cut, copy, paste my 2 command. Same, I cut, copy, paste here. You see here, same cheese. What is changing here? Only the number of filters, right? Now the same command I have repeated here. What has changed? Nothing has changed. So I can create as many as layers as I want. Why do I want more and more layers? My accuracy improves for complex data set, right? And then finally, we have our layer known as a dense layer. So dense layer is a final layer where your decisions are taken. This is your final layer here. This is your output layer. So the difference between output layer and inside layer is output layer, they are dense layer where you do your probability checks and everything, where your actual computation is happening, right? And then here you have a binary problem. So you have 1. In the last time I showed you 10, if you remember, because there were 10 outputs. And here, this is flattened. So till this thing here, this part of the code, we are till here. And this is known as feature extraction. I'm just extracting my features. I'm not doing anything, right? And then I haven't, so then there's an activation function here, sigmoid. People use softmax as well. And then you have a flattened layer, that is this layer. And then you have a dense layer that you create after the flattening is this one. Then you are creating this entire network. Any questions? So this directly not comparable to this image, this code, because this is for different code and this is a different image. Sorry about that. So that's why we have extra layers here. So normally it should be flattened layer. There should not be anything here. And then you should have this final output layer. So this is just to provide you an example, right? So, right. Any questions you have? I think people, because this image comes from this one, different example, so you get kind of confused. So till the time you do not apply dense layer, you are not solving any problem. You were here in the beginning, all this code here, and you are adding layers. So this was your layer 1, this was your layer 2, this was your layer 3, because you are doing feature extraction. In the final one, we have only used here one layer, 128. So this layer should not be there, one of them, which is extra. Guys, any question? You can figure it out, right? When you do it, I will move to the code now. Can you see my code? Now I should start running this model. Okay, so is my model ready to run now? Tell me. What is left? I haven't used any compiler, any optimizer, any loss function. I just created my model. That's why I pressed the run. It did not give you any output. Is that true? Right? Yeah. Great. So now I'll do something called compile. And I have compiling my model. And now it's running. I gave it for 10 epochs. And now it's running. It's taking its time. It's taking its sweet time. What is in the compile model? Can anyone define? Tell me what is happening. There's a loss called binary cross entropy loss. I discussed easy losses with you. I did not discuss binary cross entropy loss. For all the image problem, you will use this loss. Any comments that what could be a binary cross entropy loss? So finally, in this one, you get an image of a cat, right? Or you get an image of nearly looking cat. So binary cross entropy loss is basically telling you the probability of difference between real cat and nearest looking cat. This is there we include something called your probability things. Now matrix that we are looking for accuracy. Now your optimizer is Adam. So this is an optimizer where you do gradient descent. And there are different names to it. You will 99% use Adam. If you want, I can present to you next slide that what are different optimizers. And then you're finally fitting this model that you created. So you created this, a Z type of model or X type of model. Now you are putting this model on your data. That's why you're just trying to tell, hey, fit my model on the training set. I want epochs 10 and I was validation test set. Now, for the people who don't understand epoch is something that, if I'm teaching you today machine learning, you have understood one time the entire thing. Now, tomorrow you would sit again and revise it. This is the second time. On other day, you would sit again, third time, fourth time, fifth time. You will go through the same data again and again, revise. And this is something equivalent to an epoch, where I'm sitting and revising. And I'm going through the entire data. So more epochs I have, more accuracy I will have. But what could happen if I increase the number of epochs too high? There's the problem of overfitting. That means my algorithm is going through the data many, many times, right? Yeah, there is a problem of overfitting. So this thing is there, it's running. Just a second, I have run the code for you guys. So that because it would take at least half an hour to run, we have a lot of images. So this code is already, I ran this morning, and this is the final training and validation accuracy you have. So you see, as the epochs improves, your accuracy improves. This is nothing, this is PLT, 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 PLT. That means I have plotted different things. I have plotted my training accuracy, validation accuracy, epochs, this thing. This is simply, your easy programming. You can see this curve, right? What are you seeing guys right now? Yeah. And then you're also plotting now your accuracy. Now you're also plotting your losses here. And now you have plotted your losses and you have plotted this. So what do you see from the loss curve? As it is going through more epochs, you see the loss is decreasing. The loss function, it's converging. In the beginning, it started with 45% loss. And at the end, it is at 27% loss. I ran this model for 200 epochs. It really reduces to 3% or something, the error, which was pretty good for this kind of problem. And then you started, so this is simply your predicted, this is not important, just don't follow here. just look here and we start now testing it. And when we start testing it here, if it can show me an error, because I don't know when I ran this code today or tomorrow. Plotted it. Okay. So now it is here. Now while testing it, it should run it. It shows me an error. So it is showing you it's a cat. Why it's showing me a cat? And you see after the sigmoid function, I also gave it a condition that below 0.5, it is a dog, else print it's a cat. I have applied that into my sigmoid curve that I had. I have chosen the threshold to be 0.5. So we were here, it was plotting everything. We did our curves, validation and training. The simple step to evaluate. We predicted everything in terms of our arrays, because that simply tells you the probability values, and we start testing it. Now in the testing, what we are doing, same thing, we called an image from the test site and we give it a kind of the address, and these are the images of the details that we have, because we are taking any image from internet. So we are converting it, making it, dividing by 255, normalizing it. And this is our answer here. And you can do that with many images, maybe this is wrong or good. I don't know, it is a cat or a dog. Okay, it is a cat. So my model is able to remember that it's a cat. Now let us see this one. I copied the same syntax everywhere. I'm just calling different images. Here it was image 4609. Here it was 4500. And let us see and run it. It's a cat. So my model is doing not too bad, right? But even my accuracy wasn't very high. My accuracy was here, okay, 88%. It's not bad. We're only 12% at error. With this, guys, any questions you have? You would be able to apply this thing on your voids now. If I give you a database of voids, will you be able to get around it? So with mass scarcity, I will go next class would be a little bit on optimizers, little bit knowing about the difference between YOLO, general difference, the precise difference you will tell me, but more general difference on YOLO, mass scarcity, and UNet. Would try to present you an overall, thing. With this, I call it a day. Thank you so much. We are not meeting next week, neither for the lab, neither for the class. Yes, everyone has a good Thanksgiving. Bye-bye.
Thanks, Shradha. Bye.